Some of the finite structures considered in graph theory have names, sometimes inspired by the graph's topology, and sometimes after their discoverer. A famous example is the Petersen graph, a concrete graph on 10 vertices that appears as a minimal example or counterexample in many different contexts. Individual graphs: Balaban 10 cage, Balaban 11 cage, Bidiakis cube, Brinkmann graph, bull graph, butterfly graph, Schwartel graph, diamond graph, Dürer graph, Ellingham-Horton 54 graph, Ellingham-Horton 78 graph, Herrera graph, Franklin graph, Frucht graph, Goldner-Harary graph, Groch graph, Harry's graph, Harry's 1 graph, Herschel graph, Hoffman graph, Holt graph, Horton graph, Kittel graph, Markstrom graph, McGee graph, Meredith graph, Moser spindle, Susley graph, Poussin graph, Robertson graph, Sylvester graph, Tut's fragment, Tut graph, Young Fibonacci graph, Wagner graph, Wells graph, Wiener-Araya graph. Highly symmetric graphs. Strongly regular graphs. The strongly regular graph on V vertices and rank K is usually denoted SRG. Klesch graph, Cameron graph, Petersen graph, Hall-Janko graph, Hoffman-Singleton graph, Higman-Sims graph, Paley graph of order 13, Schreikander graph, Schlafly graph, Brouwer-Hemers graph, local McLaughlin graph, Perkel graph, Gewertz graph. Symmetric graphs. Asymmetric graph is one in which there is a symmetry taking any ordered pair of adjacent vertices to any other ordered pair. The Foster census lists all small symmetric 3 regular graphs. Every strongly regular graph is symmetric, but not vice versa. Eward graph, Mobius-Cantor graph, Papis graph, Desargues graph, Nauru graph, Coxeter graph, Tut-Coxeter graph, Dyke graph, Klein graph, Foster graph, Biggs-Smith graph, Dorado graph. Semi-symmetric graphs. Folkman graph, Gray graph, Ljubljana graph, Tut-12 cage graph families. Complete graphs. The complete graph on vertices is often called the clique and usually denoted, from German complete. Complete bipartite graphs. The complete bipartite graph is usually denoted. See the section on star graphs. The graph equals the 4-cycle introduced below. The utility graph. Cycles. The cycle graph on vertices is called the end cycle and usually denoted. It is also called a cyclic graph, a polygon, or the end-gon. Special cases are the triangle, the square, and then several with Greek naming: pentagon, hexagon, etc. Friendship graphs. The friendship graph Fn can be constructed by joining n copies of the cycle graph C3 with a common vertex. Fullerene graphs. In graph theory, the term Fullerene refers to any 3 regular, planar graph with all faces of size 5 or 6. It follows from Euler's polyhedron formula, V, E plus F equals 2, that there are exactly 12 pentagons in a Fullerene and V, 2 to 10 hexagons. Fullerene graphs are the Schlegel representations of the corresponding Fullerene compounds. 20 Fullerene, 24 Fullerene, 26 Fullerene, 60 Fullerene, 70 Fullerene. An algorithm to generate all the non-isomorphic fullerenes with a given number of hexagonal faces has been developed by G. Brinkmann and A. Dress. G. Brinkmann also provided a freely available implementation, called Fugen. Platonic solids. The complete graph on 4 vertices forms the skeleton of the tetrahedron, and more generally the complete graphs form skeletons of simplices. The hypercube graphs are also skeletons of higher dimensional regular polytopes. Cube, octahedron, dodecahedron, icosahedron, truncated solids, truncated tetrahedron, truncated cube, truncated octahedron, truncated dodecahedron, truncated icosahedron. Snarks. A snark is a bridgeless cubic graph that requires 4 colors in any proper edge coloring. The smallest snark is the Petersen graph already listed above. Blainus. A snark Blanisser Snark, Double Star Snark, Flower Snark, Loopkine Snark, Loopkine Snark, Shakeris Snark, Tietze graph, Watkins Snark. Star-A star SK is the complete bipartite graph K1, K. The star S3 is called the claw graph. Wheel graphs. The wheel graph Wn is a graph on n vertices constructed by connecting a single vertex to every vertex in a cycle.